It's now time to talk about part 3 of the LockManager app case study, which focuses on another dimension of the server structure and functionality. In particular, this lesson will give an overview of the semaphore algorithm that's implemented using Java ArrayBlockingQueue. LockManagerService uses the ArrayBlockingQueue to provide a semaphore implementation. In other words, to manage a fixed number of permits or locks that can be used to mediate access to a shared resource. Let's take a look at an example that I'm familiar with from my days as a graduate student at the University of California, Irvine, where we would go down to the Corona del Mar State Beach on the weekends and play volleyball. And the way things worked was we would have a certain number of nets, let's say there were 10 nets or so, and maybe 30 different teams who wanted to play. So at any given point, there would be more teams who wanted to play than there were available nets. So that was the limited resource, was the number of nets. And the way we dealt with this was by using a semaphore-like abstraction, where we had a bag of balls, volleyballs in this case, and there was one ball for each net. And so what would occur would be each pair of teams would send down a representative to get a ball. If they came down there and there was no balls in the net, they had to wait or block till there was a ball put back. If there was a ball available, they would take the ball, go find a net, the teams would play, then they would come back and put the ball back in the net. So this idea of having a fixed capacity that limits the number of concurrent accesses is at the heart of what a semaphore is. We're going to use the array blocking queue to manage locks in a multi-threaded program, because this is a nice way to ensure thread safety and atomic acquire and release operations without having to understand all the vagaries of Java synchronizers. So let's talk about how this actually works in practice. We're going to start by first talking about the initialization phase, where we're going to create an array blocking queue with a capacity that's equal to the number of permits. And you can see here we say new array blocking queue inside the create method. Now we're on the server side, of course, in the service, and we pass in the number of permits. We also pass in the value true, which indicates that we've initialized this array blocking queue to be so-called fair. And all that means is that threads that are waiting to acquire a permit will acquire them in the order requested, in essentially first in, first out order, that thereby preventing starvation. We make sure everybody gets a chance to go. It's fair. And we also fill the queue with lock objects, where each lock object represents a permit. And we'll look at the make locks method when we walk through the code in more detail. We then define a lock manager, as you see here, that will keep track of the array blocking queue objects that we've allocated. And as you can see, we're going to pass in a method that will generate a unique ID and the permit count to the lock manager. And then we store that lock manager in the mLockManager map along with the available locks. And the very final thing we do is return the lock manager back to the client so that it can differentiate each of the different semaphore instances. So lock manager in this case is a user-defined type, and we're passing it back using the magic of Spring and its ability to pass around Java objects that are typed on both the client and the server. There's a couple of async acquire operations. Let's take a look at the first one that will just acquire a single lock. Recall that this method is called back by the controller's acquire method, and remember it passed in the callback object as the second parameter. So we mark this method with the async annotation, and that means it's going to run in a background thread, and that background thread will be created automatically by the bean that we have auto-wired so that that will be handled for us. And if you take a look here, what's happening is that the worker thread that the request came in on for the controller is going to be running. It will then end up invoking the acquire method in the service that's shown here in its own virtual thread. So that indicates that that's what should happen, and we wired the beans together to make sure it did the right thing. Therefore, acquire, this version of acquire, the one that's running in the service, doesn't block the calling thread, namely the one that was coming from the controller, while waiting for the lock to become available. So we're not going to block in this thread. The virtual thread will not block. The virtual thread can block, but it's not going to end up blocking the HTTP worker thread, which is now returned and gone on its merry way. So the acquire method here first tries to obtain a lock by polling array blocking queue. Poll is the method that doesn't actually block. It just checks to see if there's an available lock or permit. If there is, in other words, if we don't get back a null, we're successful and we can go on to the next step. However, if no lock was available through polling, we're then going to call the take method on the available locks array blocking queue, which will in fact block, waiting for some other thread to release at least one lock so that we can then take it out of the array blocking queue. In any event, whatever happens, whether we got it right away through non-blocking or we had to wait, after we have successfully acquired the lock, then we notify the caller using this callback interface to invoke, saying we have succeeded in acquiring the lock. And that will then turn around and trigger the underlying Spring framework to send back that lock as the result for that deferred request back to the client. Let's now take a look at the more complicated async acquire operation. This is the one that is going to take a permits count. And this is called by the LockManager controller to acquire multiple lock permits. So what it's going to do is it's first going to create a deferred result object, which will hold the result of the future acquisition. So we make ourselves a deferred result, which is going to be a list of locks. And that will allow the acquire method to return as quickly as it possibly can. It's going to go back to the controller, and then the controller will return so that HTTP worker thread will not be blocked for very long at all. Here's what happens. What happens in this case is we're now going to manually submit a runnable, and that will then run in the background, and that will continue running, doing the multiple permit or multiple lock acquisition while the worker thread can go back to do something else. So this runnable task that we're going to create here will be submitted to the async task executor that we auto-wired to the mExecutor field shown here, and that will allow us to acquire the specified number of permits in the background. Let's now take a look at the getRunnableFactor method that returns a runnable. As you may recall, a runnable is a functional interface that has a single method called run that takes no parameters and returns no result. The way we're going to use that in this particular example is we're going to have a loop that will try to acquire the required number of permits by polling the ArrayBlockingQueue passed as the avail locks parameter. And you can see here, while we have not achieved the number of permits, which are also passed here as a parameter, we're going to keep looping, calling try acquire, passing in the available locks that we have in the ArrayBlockingQueue and the locks that we're trying to build. And this will keep going until we get what we want. Let's go take a look at what try acquire does. So try acquire, as you can see, takes that ArrayBlockingQueue and the locks list we're trying to build up, and it's going to ensure that this task either requires all the required permits or none, thereby preventing partial acquisitions that could lead to deadlocks or resource starvation, which is one of the subtleties of trying to implement a concurrent distributed semaphore, where we have multiple clients calling acquire, trying to acquire multiple locks simultaneously. So the way this is going to work, this try acquire, is it's first going to try to poll the available locks array blocking queue. If it succeeds and it's able to get something in there, that means there was something there, wasn't empty, it's going to add it to our locks parameter, and then we're going to return the locks.size size. And that will be an indication back over here as to whether we've achieved what this loop is trying to do. So if we get the number of permits, we're done. However, if we're not lucky enough to get a lock, then we're going to release all the locks we've acquired up to this point in one fell swoop using the for each method, releasing them all in a non-blocking way. We're then going to clear the list of locks we've been trying to acquire into and then return 0, thereby telling the caller, which is this loop, to keep trying. So this could actually loop for a while until we manage to get everything. And that's one of the tricky issues of trying to implement this type of wait-free synchronization. So the long and the short of it is that this loop will continue until all the permits are acquired, even if this requires many iterations. And that's one of the properties of this type of lock-free, non-blocking algorithm. When we're done, we're going to end up setting the deferred result parameter to the locks that we achieved, the list of locks, and that will then in turn trigger the underlying Spring platform to return this list of locks back to the client as the return result. And then finally, we'll return, after submitting the acquisition task after that's all done. This is what happens back on the controller side, so the HTTP worker thread can be recycled right after acquire returns. All the other stuff we just talked about takes place in the background, but we're going to return from the controller right away. So the final pieces of the puzzle here involve the release operations. There are two of them. The first one we're going to look at here is going to be called when a client wants to release a single lock. And the idea here is to put the lock object back into the array blocking queue. What we're going to do, as you can see here, is we're going to call the offer method on the available locks array blocking queue implementation that we fished out from the LockManager map. And we're going to have that automatically return the lock. Now, this should work if we've followed the protocol, if the client has followed the protocol and is not trying to do things like release a lock multiple times. This, however, guards against that. And if we try to put a lock back and the queue is full, then that means something's going to rise. So we're going to return a flag back to the client indicating that there's a problem. The second release operation is going to support releasing multiple locks at once. This turns out to be much simpler than trying to acquire multiple locks at once. Once again, what it's going to do is it's going to essentially take the locks parameter that's passed to it after we get the available locks from the LockManager, and then we're going to go ahead and make a stream call to turn the locks list into a stream, and then we're going to go ahead and call the offer method, which will do a non-blocking return to the underlying array blocking queue. And if anything goes wrong here, then it's going to have a false, which means it will return false from this call. That will only happen if somebody doesn't obey the protocol properly for using a distributed semaphore. Again, by trying to release something multiple times when it was only acquired a smaller number of times. So that's the end of part 3 of our discussion of the server structure and functionality in the LockManager app case study.